Okay, let's talk about work, energy, and power. This topic has got one of the weird physics things going on when we talk about work, because we use work in everyday life, but work in physics and work in everyday life is not the same. So that sometimes makes this topic a little bit confusing. Okay, so the things in this topic are definition of work, the work-energy theorem, and the conservation of energy with non-conservative forces present, and power. So we're going to go into all of these. This one's basically got to do with friction. Okay, so let's have a look here. What do we know about work in physics? If you are stuck in your house in lockdown and you can't exercise by running around the block, and you stay in your house and you jog on the spot for 6 hours, in physics you will have done no work because you did not displace. But the moment you get out your house and you walk in a straight line somewhere, you have done physics work. Okay, so work in physics is not the same as work in real life. Jogging on the spot, zero work in physics. Going for a slow stroll from A to B, working in physics. So that's the first thing to get your mind around, that unless you are displacing in a direction, you are not working. And all of this topic, the work, energy, and power topic, is based on these principles. Energy can't be created or destroyed. If you want to do work, you have to have energy. And when work is done, the work is converted into other forms of energy. So work and energy are very similar. So work is converted into other forms of energy like kinetic or potential energy. And this part at the top, energy can neither be created nor destroyed, works with this conversion of energy here. And in grade 10 you were supposed to do this conversion of energy theory where kinetic energy and potential energy are changed. So like it's often with if you drop something off the top of a building, not vertical projectile motion, but they'll say to you a ball on the top of the building's got so much potential energy, and when it lands on the ground all the potential energy is converted to kinetic energy. So this is an extension of that grade 10 topic. We don't do much of it in grade 11. So basically you jump from grade 10 to grade 12 here. And so we do a lot of work with conversion of energy in this topic. So the definition is that work is done on an object if an applied force displaces the object in the direction that the force is applied. So if you push something and it doesn't move, you haven't done work. If you push something and it moves, you've done work, but only in the direction that the box moves or the object moves. So this is how it works out mathematically. Work is the force in newtons times the displacement in the direction of the force. Okay, so force is measured in newtons, displacement is measured in meters. So we should actually have a unit of a newton meter, but in actual fact the newton meter gets converted to a joule. So everything is measured in joules, and work is a scalar. So it's not a vector, you just need the unit, you don't need a direction as well. But the direction is considered in this displacement here, but the final work answer is always a scalar. So here is the formula. Work is the force times the displacement in the direction of the force. But sometimes we are applying a force, the object is moving, but the force is in a different direction to the way the object is moving. Think of all those Newton's laws questions where there's a box and somebody's pulling the box with a rope and the box moves in one direction even though the rope's got a vertical component to it. So we take this as F delta X cos theta, which is the angle between the force and the displacement. Okay, so we're going to look at some examples to explain what's going on here. Oh, and then look in this formula, it says here cos theta. Why do we use cos theta and not sine theta? If you look at the graphs of cos theta and sine theta, if you are at 90 degrees, the cos of 90 is 0, okay? So this means if you're pulling a box this way and you have a vertical string this way, the vertical string is at 90 degrees to the direction the box is moving, and that force is not going to do any work. That's just the way it goes. If the force is at 90 degrees to the displacement of the object, no work is done. So you know, we said a joule is a Newton meter. So a Newton is defined as the force that would give a mass of 1 kilogram and acceleration of 1 meter per second, okay? So that's what a Newton is. So this ties back into Newton's second law. I don't know why that slide is there. I forgot that it was there. It's kind of irrelevant, but Newtons are actually defined using forces. Okay, so now, when will we do work on an object and when won't we do work on an object? Obviously, in lockdown, jogging on the spot, you're not working at all. Lockdown's finished, you run around the block, then you've done some work, okay? So no work is done on an object if you don't apply a force. I mean, this makes sense. If a box is sitting on a table and no force is applied, it's not working. There's no work done if the box doesn't move, if there is no displacement. Something has to move for work to be done. And no work is done if the force and the displacement are perpendicular to each other. Now this is where half of the weirdness comes in, because you have to think about which way the object is moving and what are the forces acting on it, and see if there are forces that are perpendicular or parallel or at an angle to it. And so this last part also relates to that cos theta in the equation for work. So let's have a look here at this situation. Here's a guy or a woman, it's a woman, pushing a box, and she's pushing the box with a force that is going this way and the box is moving this way. So this woman is doing work on this box. Now this woman's got a satchel on her back, or a rucksack, or a backpack, or whatever you want to call it, because I know you don't like me using that word, satchel. So she's picked up this bag on her back, and it's on her back, but look, which way is she going? She's not flying into the sky. She picked up the bag and then she started walking this way. There is no work being done on this bag, because the direction of motion this way is at 90 degrees to where the force is acting. Because remember, on this bag there has to be like an upward force to counterbalance the downward force of gravity. So I mean, the bag is not sitting on her back through witchcraft, it's sitting on the back because she's applying a force to it to lift it off the ground. But that force is upwards, but she's moving that way. So in physics, she is not working, okay? And if you ask any soldier who's carried a backpack on a long hike, he'll tell you he's working. But in physics, she picked up the bag and then she moved in the opposite direction at 90 degrees. She's not working. If you now look at her in the process of picking up her groceries, the groceries were on the floor. She's applying a force to lift them upwards. The bag, the force is upwards against gravity. The bag is lifting upwards. She's doing work. In this instant that she is doing work, lifting the bag, she is doing work. But the moment she starts walking forward, nope, she's not working anymore. So only now, as she lifts the bag upwards, the direction of the force and the direction of motion are the same. So then she is doing work. See here, the bag is up and then she's walking to the fridge with it. Nope, she's not working anymore. Yes, there's still a force here. There is still a force. If there wasn't a force here, this bag would be on the floor. Thank you, gravity. Okay, so there's a force upwards, but her motion is forwards. There is no work being done. So this is one of the interesting things about work in physics, and you have to think about this quite a lot. Okay, so now I don't want to make this video too long, so I'm going to start another video from here because the other ones are taking a long explanation.